Hi, it's Tuesday, June 16th, 2020. My name is Noah Seeley, and welcome to my channel. So today I thought we would finish our discussion on the Playing Atari with Deep Reinforcement Learning paper by the DeepMind Technologies research team. This is the second part and final part of my video collection relating to this specific paper. If reinforcement learning is new to you guys, or you feel as though some of the topics in this video are a bit fuzzy, I strongly recommend going to my channel and checking out my two-part reinforcement learning introduction videos, as well as part 1 on this paper if you haven't seen that yet. They're both pretty quick and offer some introduction to the definitions, processes, and ideas that are very important to reinforcement learning. If you're still feeling stuck with it after that, I've also included some great resources in the description of those two intro videos that I'd advise you to check out. With that being said, if you're feeling all ready, let's get back into the paper. As I've already mentioned, the paper today was written by the researchers shown here from the DeepMind Technologies lab and is called Playing Atari with Deep Reinforcement Learning. So without any further delay, let's jump into part 2 of this paper where we cover the deep reinforcement learning experiments and conclusion sections. So the deep reinforcement learning section basically summarizes what we talked about in part 1, how the researchers aim to find a reinforcement learning algorithm that uses a deep neural network in order to have an agent operate from visual game input, learning through stochastic gradient updates. This can actually relate back to our introduction to reinforcement learning series, where we thought of the neural network as the agent's brain. In this case, the agent lives in a predominantly visual world and only really has a visual cortex to pick up on new information. Imagine the agent is a human who is deaf and mute, basically trying to learn how to get the most success out of their life in their current situation. So basically, they'll use the agent to somehow update its state action function upon each new experience of the game, hopefully learning from each iteration in order to maximize that action value function and find the optimal solution, or in this case, the optimal strategy to play the game. The agent will also have experience replay implemented into their brain, or neural network, which basically means it can store its experiences from previous iterations and pool them all in a replay memory. Throughout the algorithm, queue updates, known as mini batch updates, are taken randomly from this pooled replay memory. So the algorithm I just described is called deep queue learning and is included in the paper shown here. They say that deep queue learning is better than queue learning used in previous studies as 1. Each step of experience is potentially used in many weight updates, which allows for greater data efficiency due to the experience replay implementation. 2. Each step is generally going to be similar during learning, thus by sampling a few instances of it for each update will take away a lot of variance from update to update and basically average a lot of the learning out. It will essentially break correlations found between local epochs. And 3, as kind of mentioned before, this averaging will smooth learning out and divergence is a lot less likely to occur. Basically, it was to avoid trends that might get the agent stuck in a bad local minimum that looked good at first because we're using a greedy policy, but ended up getting stuck up in a specific point in the environment, which was not to lead to an optimal solution. An issue they found with the finite space used for replay memory was that each new iteration overrides the oldest, which could mean overriding a very valuable iteration where a lot of learning occurred. They suggest a better implementation of this would be holding some sort of bias to keep better epochs and keep those around in the replay memory and use those only for later use in the replay memory. This subsection basically describes the data pre-processing and architecture of the specific model. I usually don't go too much into the sections like this because there are probably newer, better architectures floating around out there, or at least updates to this one, as it was published all the way back in 2013. Anyway, it's all just very specific to this one paper, but if anybody wants me to make a video on the specific architecture, please let me know in the comment section below and I'll get on that. The paper's experiment section talks about how the agent was able to successfully play 6 Atari games and that the same network was able to be used across all 6, each game being completely the same as the original implementation of it, with one slight exception. Basically, during training, the researchers standardized scoring for each game so the agent could stick with the same hyperparameters throughout and did not have to worry about scaling anything. They would train for 10 million frames, keeping the replay memory of the last 1 million frames. They also used a frame skipping method, basically meaning that the agent only performed an action every k frames, and its last chosen action was repeated for those skip frames. This essentially allows the agent to play k times more games in the same runtime as the normal amount of games without the frame skipping technique. They set k equal to 4 with the exception of Space Invaders. This is kind of a special hyperparameter as sometimes games are more sensitive to specific frame skips. So a lot of testing here is for sure required. As for performance measurement during training, keeping track of just the reward during training can be super noisy as there is a lot of variation throughout that. So instead, the team would measure the policy's estimated action function queue. This is an estimate of how much discounted reward the agent thinks it can make by following the policy it has learned thus far. Here in figure 2, we can see the reward tracking in these two left graphs and the policy's estimates in the two right. So yeah, we can see here how both graphs increase and begin to converge, but one is just much more smooth. Figure 3 here also shows how the learned value function will peak when it is about to kill an enemy with a torpedo, seen in the second image of the game, and will drop back down when the game goes back to normal. The researchers note that this shows signs of the agent learning the reward. This section ends off by basically showing that this reinforcement learning algorithm was able to outperform previous models in those 6 Atari games, as well as outperform expert human players. Overall, this shows how groundbreaking of an algorithm this is, as it was able to combine many machine learning concepts together to create a very powerful reinforcement learning agent. The conclusion section basically sums up their method of finding such success in 6 of the 7 games they've tested their agent on. They mention important aspects such as the agent's raw pixel input, its queue network, mini batch updates, and experience replay memory. And yeah, that's the end of the paper. It wasn't so bad, was it? So that concludes the second part of my discussion on the Playing Atari with Deep Reinforcement Learning paper by the DeepMind Technologies team. I hope you've learned a lot from this two-parter, as I think I'll start presenting papers in 2 parts, just so we can get the most out of them. There are also some more technical bits in today's sections that I did not delve into, so as always, I've linked all resources that I've used in the description below for you guys to check out yourself. If you feel I've missed anything or got anything wrong, please let me know in the comment section below. That's it for today. Thanks for watching. See you tomorrow.